10.5.1, using the base multiplier to find an exponential model. So definition. So we've looked at linear related data and the patterns we looked for there, and quadratically related data. And this last section now we're looking at exponentially related data. So for exponentially related data, we have constant changes in the input are associated with constant factor changes in the output. Okay, so as we're increasing, as x is going up by 1, the y's are constantly being multiplied by this base multiplier b. Okay, in this case, we can fit an exponential model to the data where f of x is a times b to the x, where again, this is that base multiplier. And remember, b has to be greater than 0, and it cannot be 1. And a is the output we get with an input of 0, because b to the 0 will be 1 times a gives us a. So that gives us our y-intercept from the graph. So suppose your table has 3 million bacteria on it, okay, highly possible at this point in time in the semester, as of 11 o'clock a.m. today. Okay, also suppose that one bacterium divides into 2 bacteria every hour on average. Okay, so the bacteria are doubling every hour. So fill in an input-output table where we're going to let t be the number of hours from 11 a.m. today. Okay, so 0 here is going to correspond to 11 a.m. Okay, and then 1 hour later, this is going to correspond to noon, 1 p.m., 2 p.m., etc. So the number of bacteria initially that they gave us was 3 million. Okay, so this is in millions, so we're just going to write a 3. And it keeps doubling. Okay, so these 3, every one of them is going to split into 2, so we're going to have 6 million. Then all of those 6 will split into, each one of these splits into 2, so now we'll have 12 million and 24 million. So again, our inputs here keep increasing by 1, and our outputs here keep being multiplied by 2. So explain why this data can be modeled with an exponential model. So in here, as input increases by 1, our output is multiplied by 2. Okay, so again, if we kept adding 2, we would have a linear model. But in this case, we keep multiplying by 2, we have an exponential model. So now we're asked to write an exponential function that describes the relationship between these two variables. So again, an exponential function means that we're after some f of x equals a times b to the x. Okay. And in this case, okay, if we use the variables that we have here, the output variable is n and the input variable is t. Okay, so we're after something that looks like this. Okay, well, to get the a and the b is the base multiplier, and a is our initial quantity at t equals 0. Okay, so from our table, the initial quantity when input is 0, the output is 3, so that's our a. And then our base multiplier was 2. So we have 3 times 2 to the t. So assuming your desk is not cleaned with cleaner and no extra bacteria are added besides the ones that are already there and multiplying, predict the number of bacteria that will be on your desk by 11 a.m. tomorrow. Okay? So by 11 a.m. tomorrow, that would be 24 hours past 11 o'clock a.m. today. So that means t is 24. And we want to predict the number of bacteria. The number of bacteria was designated by the variable n. So we have n of t. The number of bacteria at any time t is 3 times 2 to the t. Okay, so we want to know the number of bacteria after 24 hours. So we've got 3 times 2 to the 24th power. So on the calculator, let's get that into view here, we can do 3 times 2, and then the up arrow for the exponent, parentheses around our exponent, and we had 24. And we see we get this huge quantity. Again, it keeps doubling, so we saw, even after 3 hours it was 24, then 48, 96, and so on. And it's going to keep doubling like that 24 times over. Okay, so we have huge number of bacteria here. Okay, so this was equal to, so n of 24 was equal to, and we'll get some units on here too, because not only is this number big to begin with, 50,331,648, but that's still in millions. Okay, so tons and tons of bacteria here. Okay. So now, we mentioned the other day that 2 of the things that I want you to keep in mind that grow exponentially are bacteria and money. Okay, unfortunately, bacteria grows a lot faster than money. So an account earns 5% interest annually. At the start of 2013, $1,000 was placed into the account. We want to fill in the input-output table below to see the relationship between years since 2013, BRT, and the amount of money in the account, which we're going to use the variable A. Okay, so when t equals 0, this is going to correspond to the year 2013. Okay, so initially there was $1,000 in the account, and it said that it's going to get 5% interest. So if we do 5% of 1,000, 5%, percent means divided by 100, of multiply times 1,000, so we're going to get $50. So 5% of $1,000 is $50. So remember, interest is money that gets added to your account. Okay, so 1 year later we don't have $50 in the account. Okay, that would be a terrible investment. Okay, we have, this is the additional money that gets put into our account. So now we have $1,050 in the year 2014. Okay. Well, the next year we're going to get 5% of $1,050 added to our account. So we're going to take 5 divided by 100 times 1,050. Okay. And we get $52.50. Again, this is the interest, so it gets added to our account that already had $1,050. So if we add that to the account balance, we get $1,102.50. Okay, so one more. So now we're going to take 5% of our new balance, $1,102.50. And so again, we're going to take 5 divided by 100 times $1,102.50. And we're going to get $55 and 125th thousandths here. So if we add that to what's already in our account, we get 1157.625. Now, these numbers, it might not be obvious what the pattern is here. Okay, here we can see that t keeps increasing by 1. Okay, but here, if on the calculator we were to take, so let's take that end number we got there. So let's take that 1157.625 and divide by the previous number, which was 1102.5. We get 1.05. And if we take that 1102.5 and divide by previous number, 1050, we get, well, we would have got, had I typed correctly, let's try that again. So 1102.50 divided by 1050, and we get 1.05 again. And now if we take that 1050 and divide by the previous output, which was 1,000, yet again get 1.05. Okay, so what does that mean? That means in the backwards direction we kept dividing. So here, again, to get from one entry to the next, we would multiply by 1.05. So 1,000 times 1.05 is 1050, times 1.05 gives us the next output, times 1.05 gives us the next output. So the input is increasing by 1 each time. And to get from one output to the next, do we need to add some constant or multiply by some constant? And here we're multiplying. Okay, we were not adding a constant amount to the account. First we added $50, then we added $52.50, and then we added $55.12 to the account. So we were not adding a constant amount. But it does turn out that we happen to be multiplying by a constant amount. So these data are exponentially related, which means there is an exponential function that describes the relationship between them. Okay, so this exponential function, we need an a times b to the t. Okay, so again, our base multiplier in this case was 1.05. And that initial starting quantity when the input was 0, their output was 1,000. Okay. So this gives us a mathematical equation that describes the relationship we see here between the input and output variables. Okay, so you can try it. We can plug in 0. We'll get 1,000 times 1, which is 1,000. When you plug in 1, we're going to get 1,000 times 1.05. And we'll see that that comes out 1,050. And then for the next one, if we take 1,000 times 1.05 to the second power, we will get this 1102.50, and so on.